Find the Fourier Sine transform of 1 by x into a square plus x square. We know Fourier Sine transform of f of x is given by f s of f of x, which is equal to fs bar of p, which is equal to root of 2 divided by pi integral 0 to infinite f of x sin px dx. That is equation number 1. Let small f of x, which is equal to 1 by x into a square plus x square. That is equation number 2. From 1 and 2, Fourier sine transform of 1 by x into a square plus x square, which is equal to fs bar of p, which is equal to root of 2 divided by pi integral 0 to infinite 1 by x into a square plus x square sin px dx, replacing f of x by 1 by x into a square plus x square in equation number 1. This is equation number 3. Now differentiate both sides with respect to p. We have different d by dp of fs bar of p, which is equal to d by dp of root of 2 by pi integral 0 to infinite 1 by x a square plus x square sin px dx. So that is equal to root of 2 divided by pi. So without loss in generality, we are changing integral and differentiation. So we are taking the differentiation inside the integral. So integral 0 to infinite 1 by x into a square plus x square d by dp of sin px dx. Only the term sin px is having the variable p. That is why the differentiation is applicable only for sin px. It is equal to root of 2 divided by pi integral 0 to infinite 1 by x into a square plus x square. The differentiation of sin px, x cos px into x, right? So differentiation of sin cos, then differentiation of px, you will get x with respect to p. That is why we are getting x cos px dx. So d by dp of fs bar of p, which is equal to root of 2 divided by pi integral 0 to infinite 1 by a square plus x square, x and x get cancelled. So x cos px, there is x in numerator, and x into a square plus x square, that x is in the denominator. So cos px dx, that is equation number 4. Now consider the integral 0 to infinite 2y e power minus a square plus x square into y square dy. Let a square plus x square into y square equal to t. Therefore dt, which is equal to a square plus x square 2y dy, differentiation, right? Both side, keeping a and x as a constant. So 2y dy, which is equal to dt by a square plus x square, right? Therefore next we are considering the limit. When y is equal to 0, t is also 0. When y is equal to infinite, t is also infinite. So there is no change in the limit. 0 to infinite 2y e power minus a square x square y square dy becomes integral 0 to infinite e power minus t dt by a square plus x square, which is equal to a and x are constant because this integration is with respect to t. So taking outside 1 by a square plus x square from the integration, so you will get 1 by a square plus x square root integral 0 to infinite e power minus t dt. So we know e power minus t, integration of e power minus t is minus e power minus t, lower limit 0, upper limit infinite, which is equal to minus 1 by a square plus x square. Applying the upper limit e power minus infinite minus lower limit 0, e power minus 0. E power minus infinite is 0, e power minus 0 is 1, minus 1 by a square x square, 1 by a square plus x square, 0 minus 1. So minus into minus plus, you will get 1 by a square plus x square. This is what integral 0 to infinite 2y e power minus a square x square into y square dy, right? Now this is equation number 5. Now multiplying both sides of 5 by cos px and integrate both sides between the limit 0 to infinite. So we have with respect to x, integration with respect to x, integral 0 to infinite cos px by a square plus x square dx. which is equal to integral 0 to infinite cos px dx integral 0 to infinite 2y e power minus a square plus x square y square dy, which is equal to integral 0 to infinite 2y. So we are splitting the powers of e power minus a square y square into e power minus x square y square dy. So integral 0 to infinite cos px by a square plus x square dx, which is equal to integral 0 to infinite 2y e power minus a square y square dy, keeping as on one integration, and the second one integral 0 to infinite e power minus x square y square cos px dx. This is equation number 6. Let I, which is equal to integral 0 to infinite e power minus x square y square cos px dx, right? We are taking that part of the integration, right? So that is equation number 7. Differentiate I with respect to p. We have di by dp, which is equal to d by dp of integral 0 to infinite e power minus x square y square cos px dx. So again, without loss in generality, we are taking the differentiation inside the inside the integration, and this is with respect to p. That is, then d by dp is applicable only for cos px, because no other term having p. So it is equal to integral 0 to infinite e power minus x square y square d by dp of cos px dx, which is equal to integral 0 to infinite e power minus x square y square differentiation of cos px, differentiation of cos minus sine differentiation of px, you will get with respect to p, you will get x, so minus x sine px dx. So multiplying numerator and denominator of the integrand with 2y square, so integral 0 to infinite 2y square by 2y square e power minus x square y square into minus x sine px dx, right? Now that is equal to taking 1 by 2 y square outside, right, of the integration, so equal to 1 by 2 y square integral 0 to infinite grouping minus 2x y square, right, as one term e power minus x square y square, because the differentiation of e power minus x square y square is e power minus x square y square into differentiation of x square minus x square y square is minus 2x y square. For that concern, we are doing like this, right? Minus 2x y square e power minus x square y square sine px dx, which is equal to 1 by 2 y square integral 0 to infinite sine px. The remaining term is nothing but derivative of e power minus x square y square. Now we are going to use integral u dv formula, uv minus integral v du, 1 by 2 y square uv, here u is sin px and v is e power minus x square y square, uv sin px e power minus x square y square, lower limit 0, upper limit infinite, minus 1 by 2 y square integral v du, v is e power minus x square y square into derivative of u is sin px. So which is equal to 1 by 2 y square, applying upper limit e power minus infinite 0, that term is 0, and sin 0 is 0, applying the lower limit 0, so whole term becomes 0, minus 1 by 2 y square integral 0 to infinite e power minus x square y square derivative of sin px p cos px. Here the derivative is with respect to x, so that is why derivative of px you are getting p, so p cos px dx. So that is equal to minus p by 2 y square, right, p, taking p outside the integration, so that integral is nothing but I. See, integral 0 to infinite e power minus x square y square cos px dx is I. That is from equation 7. Therefore di by dp, which is equal to minus p by 2 y square I, right? So now we are going to use differential equation idea. So di by I, so variable separable method, di by I, which is equal to minus p by 2 y square dp. So integrating both sides, so we have integral di by I, which is equal to minus 1 by 2 y square integral p dp. So di by I integration log I, which is equal to minus 2 y square integral of p, so p square by 2 plus log c constant, right, integral constant. Now grouping log one side, so log I minus log c, which is equal to minus 1 by 2y square p square by 4 by 2, that is minus p square by 2 into 2 4 y square. So log a by b, which is equal to log a minus log b. We are using that idea. Log I by c, which is equal to minus p square 4y square. So log a, if log a equal to b, then a equal to e power b. So using that idea, I by c, which is equal to e power minus p square by 4y square. Therefore I is equal to c into e power minus p square by 4y square. Now we are going to calculate the value of the constant, integral constant c. For that is equation number 8. So when p is equal to 0, I is equal to c into e power minus 0, that is I equal to c, right. Now from equation number 7, I is equal to e power integral 0 to infinite, put p is equal to 0, on that e power minus x square y square cos 0 dx, that is equal to integral 0 to infinite e power minus x square y square dx. So we know that the integral formula from the definite integral 0 to infinite e power minus a x square dx, which is equal to 1 by 2 root of pi by a. A is greater than 0. Here a is equal to y square. So using that, I is equal to integral 0 to infinite e power minus x square y square dx, which is equal to 1 by 2 root of pi by y square, that is equal to 1 by 2y root pi, right. When p is equal to 0, I is equal to 1 by 2y root pi. This is 9. From 8 and 9, so from 8 I is equal to you are putting, so e power yeah, again we are putting 0 here, so you will get c, that is 10. From 9 and 10 we have c is equal to 1 by 2y root pi. So from 8 I is equal to 1 by 2y root pi e power minus p square by 4y square. From 7 I is equal to integral 0 to infinite e power minus x square y square cos px dx, which is equal to 1 by 2y root pi e power minus p square by 4y square. So going to equation number 6, integral 0 to infinite cos px by a square plus x square dx, which is equal to integral 0 to infinite e power minus x square y square cos px dx into integral 0 to infinite 2y e power minus a square y square dy, which is equal to integral 0 to infinite 2y e power minus a square y square dy into 1 by 2y root pi e power minus p square 4y square, which is equal to root pi integral 0 to infinite e power minus a square y square into e power minus p square by 4y square into dy. So root pi integral 0 to infinite e power, grouping the powers of e minus a square y square plus p square by 4y square dy. We know that integral 0 to infinite e power minus a x square minus b by x square dx, which is equal to 1 by 2 root of pi by a e power minus 2 root ab. Here we are having a is nothing but a square and b is nothing but p square by 4. Using this formula, we will get integral 0 to infinite cos px by a square plus x square dx, which is equal to root pi 1 by 2, right, root of pi by a, root of pi by here a square e power minus 2, right, a into b, root of a square, b is p square by 4, which is equal to pi by 2 1 by a e power minus 2 ap by 2. 2 and 2 get cancelled, so which is equal to pi by 2 into 1 by a e power minus ap. So from equation number 4, d by dp of fs bar of p, which is equal to root of 2 divided by pi integral 0 to infinite cos px by a square plus x square dx. So using cos px integral 0 to infinite cos px by a square plus x square dx value. So here we will get the root of 2 divided by pi by 2 into 1 by a e power minus ab or ap. So d by dp of fs bar of p, which is equal to root of pi by 2 1 by a e power minus ap. Now integrating with respect to p, we have integral d by dp of fs bar of p dp, which is equal to integral root of pi by 2 1 by a e power minus ap dp. So this left hand side becomes fs bar of p, because we know derivative of fs bar of p, which is equal to fs bar of p. Integral derivative of fs bar of p, sorry, right? So we know integral dx is x. Instead of x, you are having fs bar of p. Integral derivative of fs bar of p is nothing but fs bar of p, which is equal to, so root pi by 2 is a constant, 1 by a is constant, take it outside from the integration, root pi by 2 1 by a integral e power minus eap dp. Using integral e power minus ax formula, integral e power minus ax, which is equal to e power minus ax by minus a. Using that, we will get root pi by 2 1 by a e power minus a p divided by minus a plus c1, where c1 is the integral constant, right? So this is next equation, that is equation number 11, right? When p is equal to 0, 11 implies fs bar of 0, which is equal to root of 5 by 2 1 by a e power minus 0 by minus a plus c1, that is equal to minus root pi by 2 1 by a into a square plus c1, that is equation number 12. But from 1, fs bar of 0, which is equal to 0, right? That is 13. From 12 and 13, minus root pi by 2 plus 1 by a square plus c1 equal to 0, right? This implies c1 equal to root pi by 2 1 by a square. Using this c1 value in equation number 11, we have fs bar of p, which is equal to root of pi by 2 1 by a e power minus ap by minus a plus root of pi by 2 1 by a square. That is minus root of pi by 2 1 by a square e power minus ap plus root of pi by 2 1 by a square. So therefore, Fourier sine transform of 1 by x into a square plus x square equal to fs bar of p, which is equal to minus root of pi by 2 1 by a square e power minus ap plus root of 1 by a square root of pi by 2 into 1 by a square. So we can grouping this, right? So root of pi by 2 1 by a square is common, take it outside, you will get root of pi by 2 into 1 by a square into 1 minus e power minus ap, which is the Fourier sine transform of the given function, right? Thanks.